Okay, sigma bonds and pi bonds. All right, so now how can we determine from a molecule? Okay, so for example, if we have a double bonds, and this guy is called a formaldehyde. Okay, formaldehyde. Do you know what is that? Formaldehyde, CHO. Okay, CH2O. And this guy is used to preserve the dead body. Okay, the formaldehyde. Okay, so if you're talking about the carbon over here, they have two single bonds over here, and each of the single bonds are sigma bonds. Those are sigma, and this is also sigma. And they also has the double bonds over here. So generally, double bonds containing, they have a two bond over here, right? Double bond containing one sigma bond plus one pi. So generally, this is what happened for the sigma, for the double bonds over here. They have a one sigma and one pi, and this is a double bond, okay? But if you have a triple bond, two bonds, they have three of the bonds over here, and one of this is a sigma, and two of those are pi. Okay, two of those are pi. So triple bonds containing one sigma and two pi's. Okay, so this is generally what we talk about for the MO theory. And in general, they are just going to ask you one of the questions. For example, we have this molecule here. How many sigma bonds we have? How many pi bonds we have in this molecule? Then you see, okay, you have two of single bonds, and each of those are sigma. So we generally, you can make a list. How many single bonds have? How many double bonds do we have? Sigma single bonds, we have two single bonds over here, and we have one double. So two single bonds means two sigma, and one double bonds means one sigma plus one pi. So now you can see totally we're going to have a three sigma and a plus one pi, right? So that is generally the result. If the question asking you how many sigma, how many pi, X. Okay, yeah. Well, this is a simple example. Then let me just give you one complicated example. Okay, so now this is acetic acid. Okay, so how many sigma bonds, how many pi bonds that in this compound? Well, then you just need to count. Okay, how many single bonds do we have? How many double bonds do we have? Single bonds means how many sigma? Okay, one. Double bonds means one sigma, one pi. Then generally you can figure out how many sigma, how many pi shows over here, right? So if you're talking about a single, how many single do we have? 1, 2, 3, 4, 5, 6. So we have a 6 single, and 6 single means 6 sigma. And how many double do we have? And we have one double. One double bonds means one sigma plus one pi. So totally, if you add them together, you have a 7 sigma plus one pi. Are we clear? Okay, so generally this is what the question asking for. Okay, so now I'm going to draw this. Okay, so this is a benzene. how many sigma, how many pi, how many sigma this molecule has. This guy, each of this actually is a carbon. Each of the dots means a carbon. Okay, so that's just a carbon, 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 carbon. And here, this is double bonds. On this line, this is single bonds, double bonds, single bonds, double bonds. They make a ring over here. Then you can see how many sigma, how many pi. And just count how many single they have, how many double they have. Single bonds, 1, 2, 3. So now this guy has the 3 sigma, right? 3 single bonds. How many double? 1, 2, 3. Also 3 double. So 3 single bonds means 3 sigma. 3 double bonds means 3 sigma plus 3 pi. Make sense, right? And then you add them together. This guy has a 6 sigma plus 3 pi. Are you clear? Are you clear? Okay. And don't forget triple bonds. This is called alkyne. The alkyne. How many sigma, how many pi it has? This guy do not have a double bonds, but they have a triple bonds. Single bonds, they are having 2. Triple bonds, they have a 1. So 1 triple bonds means 1 sigma. Okay, 1 sigma plus 2 pi. Okay, it has a 1 sigma plus 2 pi, and 2 sigma, 2 single bonds means 2 sigma. So totally, this guy has 2 sigma plus 2 pi. Okay, so this is how we count the sigma bonds and the pi bonds. Any questions? No question? Okay, yeah. So this is the MO theory that we're talking about. Generally, they're asking you how many sigma bonds they have, how many pi bonds they have. Okay, and then we're going to talk about hybridization. Okay, hybridization. And again, we talk about hybridization is not a theory. Hybridization is a patch for MO theory. Hybridization is a patch for MO theory. Okay, so we first we need to explain. Okay, so why the hybrid? What is the MO theory? MO theory is talk about if you have the orbit a single electron in your orbital, then this single electron can paired with others to making a bonds. One of the example is just oxygen, right? The oxygen is a 1s2, 2s2, and 2p4. So if you draw the electron diagram for the oxygen, it's just 1s, 2s, and 2p. So they have a single electron, a double. So this is the electron diagram for oxygen, right? The 4 electrons in the p. And then you can see this guy has 2 single electrons, unpaired electrons in the p orbital. So that's why those 2 single electrons would like to pair with others to making bonds, right? And then so that's why the oxygen, they are having a chance to making a bond like this, right? Yeah. So they can making 2 single bonds, right? 2 unpaired electron can making 2 single bonds, right? Two of the sigma bonds, or they can making 1 double bonds over here, right? And we talk about the double bonds is made of 1 of the sigma and 1 of the pi. So p orbital can making sigma bonds, and also p orbital can also making a pi bonds. That makes sense, right? So that's why oxygen can have this on those two options. Either they are making two single bonds or making one double bonds. And this is the perfect for oxygen because they only have two electrons. So they only need two paired electrons. That makes sense, right? So this is very good to explain oxygen, but not for carbon. Let's see why. And so this is a mystery for carbon. So that's why people need to explain that. 1s2, 2s2, and 2p2. This is carbon. Carbon only has 6 electrons. So if you draw the electron diagram, one S, 2s, and 2p. So this is the carbon electron diagram. Then that's gonna be okay, based on the MO theory, if you have one single electron, then you're going to pair one bond. So here, carbon only have two single electron, and there's no electron in one of the empty orbital, p orbital. So does that mean the carbon can only making two bonds? Makes sense, right? But if you're based on the MO theory, yes. Is that right? So that's why then that's gonna be hard. Okay, so if the carbon can only making two bonds, where it is coming from? Where the methane coming from? Where the methane coming from? We know the carbon can making a bond with 4 hydrogen, right? So this one is hard to explain. So that's why we talk about, I'm calling this as a patch, because the scientists need to explain the methane with the MO theory. So that's why the hybridization is coming out. Well, but it turns out that makes sense. Everything can be explained by the hybridization. So what is that hybridization? They said, okay, now the carbon need to bond with the 4 of the hydrogen. So first, they're doing the promotion. It's called a promotion, which means one of the hydrogen, one of the electrons in the carbon in 2s will be promoted to the 2p orbitals. So now you're going to have 4 of the single electrons up there. One of the electron in the 2s will be promoted to the 2p orbital, right? And then now you're going to have the 4 of this. But the point is, even we have a 4 of those single electrons, it's still not good enough, because if you're looking at the methane, all of those 4 bonds are identical, which is exactly the same. That makes sense, right? But the 2s and 2p, they are having the different energy level. 2s has a lower energy than the 2p. So those 4 single electrons is not identical. So that's why they said, okay, now we're going to form this kind of structure, we need to have a hybridization. In another word, we're going to hybridize the s orbital and the p orbital together to making a bond. Okay, we're gonna hybridize. So in this case, we're still has a 1s, but we're going to hybridize the 2s and the 2p all together. Instead, we call this is 2p orbital or 2s orbital. We give it a special name. This is called a hybridized orbital. And this hybridized orbital is called sp3 hybridization. Okay, because the s means one of the s orbital, p3 means 3 of the p orbitals. So 1s plus 3 of the p altogether making 4 hybridized orbital. So this is called a sp3 hybridization. Okay, so sp3 making 4 hybridized orbital. Then in this case, they are going to have a 4 single electron in a same level. in the same identical energy level, then those are 4 orbitals are exactly the same. Then what is the shape of the hybridized sp3 hybridization? They have a 1. It also has a similar like a lobe of the p orbital, but the other side is much bigger. So generally, this is the hybridized orbital, the shape of the hybridized orbital, something like that. Okay, and usually the hybridized orbital can only making sigma bonds. So that's why. So in this case, this guy has 4 of those hybridized orbitals, and then they can only making 4 sigma bonds. And then here you see methane has 4 single bonds, and each of those are sigma. So those are hybridized orbital can only making 4 sigma bonds over here. So this is one type of the hybridization we call the sp3 hybridization. Are you clear? Okay. And then there's some other case you can hard to explain. For example, just like the formaldehyde that we're hard to explain. If we're using sp3 hybridization, then it's hard to explain this because this hybridized orbital can only making sigma bonds. And this is double bonds. They containing 1 sigma and 1 pi. Then this one definitely is not going to explain that. Then they say, okay, so if we have this situation, we're changing the hybridization. It's not going to have the sp3 hybridization. Instead, they're going to have it's called a sp2 hybridization. So in this case, so anyway, we're having 1s and 3 of the p, 2p. But right now, we're still going to leave 1s alone, but we're going to hybridize 1s orbital and 2 of the p orbital together, then making the sp2 hybridization. That means 1s and 2 of the p. Then they left the other p, they left out the other p out, right? So in this case, now we can explain this. 3 of the hybridized bond orbitals can making 3 sigma bonds, right? So in the central atom carbon, we do have 3 sigma bonds, right? This is sigma, and 1 of the sigma in the double bonds. And the p orbital, the 2p orbital can making 1 of the pi bonds. So this one making a pi, and this guy making 3 sigma, and then it can explain this. It makes sense, right? Okay. Remember, pi bonds is made by side of the 2p orbitals. Okay. Side by side 2p orbitals. So this one can explain this one. And then there's another situation like this. We have a double bonds, and this is alkyne. Okay, how to explain the central atom over here? Well, then this situation, sp2 hybridization, it doesn't work, right? Since this guy has a 2 in the central carbon over here, they have a 2 sigma bonds and 2 pi. Then how can we explain this? Well, then that's gonna be another different kind of hybridization. And this is called a sp hybridization. And then they left the 2 of the p orbitals. 1s still over there. So we only just need sp. Instead of sp2, we need sp. So 1 of the s orbital and 1 of the p orbital hybridize together to making 2 identical sp hybridization. And then we left two of the p orbitals alone. So in this case, two of the sp hybridization can making two sigma bonds, and two of the p can making two pi bonds. Then we can explain this, right? We have a 2 sigma and 2 pi. Okay, so in general, you don't have to remember too detail about this, but just let you know how this is where the hybridization comes from. Okay, we try to explain how we making those bonds. Okay, but the rest of parts is what I'm going to talk about in detail. How do we determine hybridization? How do we determine a hybridization for a molecule? So generally, you just need to determine the electron domain. As long as you know how many number of the electron domain, If you know the number of electron domain, you know the hybridization. For example, if we have a 2 electron domain, so what does that mean? 2 electron domain just like this. You see? If we have a central atom, central carbon, and they have a 3 electron and one double bonds, one triple bonds, one single bonds, or 2 double bonds, then this guy has a 2 electron domain, right? This guy has 2 electron domain, then that's going to be sp hybridization. So it doesn't matter, even we have this situation, even we have this is also 2 electron domain, 1 triple bonds, 1 lone pair. This is also a 2 electron domain. As long as we have a 2 electron domain, those are all sp hybridization. 2 electron domain, how to remember this? Easy to remember. This is a 1s and 1p add together making 2. So 2 electron domain making sp hybridization. This is how I remember it. Okay, sp, 1s, 1p add together making 2. So that's referred to 2 electron domain. If you have a 3 electron domain, one example is, okay, we have a double bonds, single bonds. This is a 3 electron domain. Or like oxygen, they have a double bonds, 2 lone pairs. This is also 3 electron domain. See, those are all 3 electron domain. So if we have a 3 electron domain, remember the lone pairs also count as an electron domain. If they have 3 electron domain, then that's going to be sp2 hybridization. Remember, 1s plus 2p together making 3. So they have a 3 electron domain. Is it easy to remember? Okay, so sp2 means 1s plus 2p, and add together making 3. So that means a 3 electron domain give your sp2 hybridization. This is one example. So if you have a 4 electron domain, which means you have a 4 single bonds over here, that's a 4 electron domain, then they're going to have a sp3 hybridization. Okay, 1s plus 3p together, that means 4. Okay, so sp3 hybridization. All right, so remember, when we talk about electron domain geometry, we talk about 2, 3, 4, and 5 electron domain and 6 electron domain, right? So that means, so if we have a 5 electron domain, then can you imagine that what is the hybridization? Now remember, S, we only have 1s, but we have a 3p. So now 1s and 3p all hybridize together, then what's the next that you're going to hybridize? In the orbital, we have S, P. What's next? D. So now P, S, and P all hybridized. The next one, we're going to introduce the P orbital to hybridize together. Okay? So now this is sp3d. and D means one of the D. So five electron domain, the hybridization is sp3d hybridization. Okay, so you see one of the S, three of the P, and one of the D. So altogether, that's 5, right? And 5 means 5 electron domain. Are you clear? Okay, then 6. Then what is the hybridization is called? sp3d2 hybridization. Okay, sp3d2 hybridization. So sp3d hybridization, and then one of the example you can see xenon F2. Xenon F2, you see, this guy, xenon difluoride, the central atom xenon, they have 2 single bonds and 3 lone pairs, and they give you 5 electron domain, right? And so this guy has a 5 electron domain, then the hybridization will be sp3d hybridization. Okay, so I'm just saying, to determine what is the hybridization for the central atom, in general, we just need to looking at how many electron domain around this, including the lone pairs. Okay, not just the bond, including the lone pairs. Then once you count how many, then you will know what is the hybridization. Okay, yeah. So now I give you one example. Still, now we're having this is again, this is ethanol. Oh, sorry, not ethanol. This is acetic acid. Okay, so what is the hybridization for this carbon? sp3, yeah. That's good because this carbon has a four electron domain. So this sp3. What is the hybridization for this carbon? sp2. Okay. What is the hybridization for this oxygen? sp3. Good. Because they have 2 single bonds and 2 lone pairs, 4 electron domain. So sp3. What is the hybridization for this oxygen? sp2 hybridization. Because this oxygen has 1 double bonds, which is 1 electron domain, and 2 lone pairs. Okay, so this is sp2 hybridization. Are you clear? Now, again, what is the bond angle for this carbon? Okay, the question will test. What is the 4 electron domain? If they have a 4 electron domain, what is the bond angle? Tetrahedral 109.5. That is the bond angle for this carbon. Okay, for each of the bond angle around this carbon. What is the bond angle for this carbon? So this guy has the 3 electron domain. What is the geometry? What is it? That's 120 because this is trigonal planar. Okay, so the bond angle is 120. Okay, so this guy oxygen here, there's no bond angle because they only just 1 bond over here, so they don't have 1 bond angle. How about this oxygen over here? What is this bond angle? Not 1/8. 1/8 is a straight line, remember. But you just said this is sp3 hybridization. How many geometry? How many electron domain? They have 4 electron domain. If they have a 4 electron domain, what is this? And this guy has 2 bonds and 2 lone pairs. What is the geometry of that? We do that. That's the water, right? We talk about water. Oxygen in the central, they have 2 lone pairs and 2 single bonds. And this is 104.5. Or you can think about it as less than 109.5. It's smaller than 109.5. So you see, we draw the Lewis structure like this, but it doesn't mean the bond angle is exactly just like this. Okay, here the bond angle is really depends on the geometry of this molecule. Sense, right? Yeah, the different geometry. So I don't expect you to remember the 5 electron domain and 4 electron domain, the 5 and 6 electron domain bond angle, but you need to be clear about 2 electron domain, 3 electron domain, and 4 electron domain. What is the bond angle for those?
Is this gonna be on final?
Yeah. Okay. So that's that generally talk about the bond hybridization, bond angle, and the geometry. Those are all combined together. Okay, just give you one of the molecule, then you can based on this to determine what is the hybridization, what is the bond angle for each of this. So the real geometry of this molecule is not like this. The real geometry of this, the acetic acid is not a straight line. It has a shape. It has different shape. All right, so this is the hybridization that we talk about. Okay, so let's take a break. So in general, what we talk about is like we talk about polar and polar molecule, they have another effect, it's called a dipole. So we're going to take the testing options for dipole, you can have it as well as this is one concept we talk about. Okay. So polar molecule is has a dipole. Yes. The other one. The bottom part is this starting from our bottom. So the whole theory. And I'm going about. So and whole theory, and actually all the theory talk about if you have an optical, then it overlap together, then it's about. So generally the 2s orbital can overlap together, overlap this, it's about. And the s orbital and the p orbital also overlap together, it's about. So this SS, SP, and P and T, the overlap together, they are all the four cases of sigma bond. So this is the sigma bond constant. Okay? And another thing is the T orbital. If you are making a sigma bond, must be hand to hand, not to side by side. Side by side is called pi bond. And this is the what we talk about. So the pi bond is two of the pure positive pure on basis side by side over the Okay, so the next part, I'm going to talk, I don't want to talk too much. The next concept is called intermolecular force. Have you ever heard of intermolecular force before? Well, to be honest, if I talk about those in detail, that's going to be like a 2+ story. Okay? So, but we don't have enough time to talk about that. But I will give you some of the concept about the intermolecular force. But before we doing that, I'm going to give you do one of the examples. So what is that? I'm just making a method for it. So now we have a piece of paper. Okay, so we have a piece of paper of it. And then I'm going to fold them together. And then I'm going to cut the bottom part of this paper. Okay. So technically, if we release it, what happens? And we're making a 2 pieces, correct? Okay, let me try one more time. Say what I. Do one more time. But it's negative, right? Do one more time. So I think the paper is yes, okay, fine. Okay. So this is, and just to give you, sorry, the demo is not perfect, but you see the 2 papers connected together. Okay, and this is what happened for the force. Intermolecular force, that's called inter, which means in between the molecule. So it's not talking about the force inside of a molecule. It's talking about force in between the molecule. Okay, so this is what happens with the intermolecular force. Intermolecular force, they connect the stuff all together. So in general, but just let you know, you're not going to making this happen if you just put 2 papers together. It doesn't work. Okay, so I'm making some glue over there. So that's why we have they can glue them together. But just okay, so why people have a glue? The glue actually we're just using kind of a concept of intermediates. If you want to find a glue, a material for glue, you have to find the material is a very, very big size of the molecule. The molecule very big, and then they can stick together. Okay. So the sticky generally is represented as a strong intermolecular force. Okay, so so this is the start of the intermolecular force. Intermolecular force, IMF, intermolecular force. This is talking about the force in between a molecule. For example, if we have a 2 water molecule, and those 2 water molecules will interact together, they're going to have a force together. And this force is what we call the intermolecular force. Okay, it's not between, it's not a bond. It's talking about the force between two of the molecules. And just to let you know, doesn't matter what kind of molecule, as long as the molecule, they always has the intermolecular force. But some of the molecule has a really strong intermolecular force. Some of the molecules has a really weak intermolecular force. Okay, yeah. So this is generally is what we call the intermolecular force. And then last time, you remember when we talk about gas, liquid, and the solids, we talk about the three different phases. We talk about there is an invisible force that connect between each of the molecules, right? Right. So reason you can have the gas, liquid, and solids is because when we have the solids, the intermolecular force is there. Intermolecular force is not going to change between solids, liquid, and gas. As long as you have the same material, the intermolecular force will be the same. But the point is, the solids always represent a low temperature, relative low temperature, right? So the gas, the molecule didn't move too fast. So the energy of the intermolecular force is stronger than the energy, the mobility or energy of the kinetic energy of the molecule. So that's why they kept everything together. But for the liquids, you're going to the molecule has a higher energy, like we talk about, like you're at a teenager, and you have a higher energy, and then they have a little bit ability to move the molecule around because the intermolecular force is not as strong, is not as much stronger, is not much stronger than the kinetic energy of the molecule. But when you have a gas, intermolecular force is still not changing, but the kinetic energy of the gas molecule is much higher than the intermolecular force. So we go for freedom. Okay, so generally this is what happens we have a different three force. Intermolecular force is still there, is kept, but the gas molecule, the activity energy, the kinetic energy of the molecule is different. So then they are making three different phases. Okay, so this is generally the intermolecular force. So that's why if you're determining whether this molecule has a stronger intermolecular force or weaker intermolecular force, just need to looking at their boiling point and the melting point. Okay, remember, if you have a stronger intermolecular force, then you should have a really high melting point or boiling point, right? Because you need to have enough higher energy against the intermolecular force to making as a liquid. That makes sense, right? So if you're talking about compare the intermolecular force, in general, you just compare. You're going to compare their boiling point and the melting point. You're going to compare the melting point and the boiling point. So now you can think about, okay, so oxygen and the water, which one will has a higher boiling point? Water will have a higher boiling point, right? Because oxygen in the room temperature is already a gas. So which means that it's already boiled, right? So the boiling point for oxygen should be below than 0. But water has a 100 Celsius is the boiling point. So obviously water has a higher boiling point. And then, so that's why the intermolecular force, water should be much larger than the intermolecular force of the oxygen. Are you clear? Okay, So this is generally you can base on the boiling point or melting point to compare the intermolecular force. And how can we just determine the intermolecular force by looking their structure or looking there the molecules? So in general, non-polar molecule, if we talk about intermolecular force from weak to strong, non-polar molecule usually has a weak intermolecular force. Then it's go for polar molecule. Then it go for the ionic compounds. Okay, so you see, so that's why you see, we talk about oxygen, nitrogen, hydrogen, and chlorine. You see, those guys, fluorine, those guys, those are all non-polar molecules, right? And those are all generally, those are all gas molecule in the room temperature, right? Gas molecule means has a really low boiling point, right? Just like you're pouring, if you're pouring the liquid nitrogen on the surface, once you're pulling out, it starts boil. Okay, then the room temperature is much higher than their boiling point, so they're going to boil immediately. So that's why those guys are all non-polar molecule. So they're very weak. They're non-polar molecule, and also you see CO2 is also a gas molecule, right? CO2 is also a gas molecule. This guy also has a really weak intermolecular force. And again, CO2 is a non-polar molecule, right? For the polar molecule, well, in general, polar molecule like water, right? Water, this guy is a polar molecule, right? And also we talk about the alcohol. Ethanol. This is alcohol, ethanol. Also, ethanol is also a liquid in the room temperature, right? So this guy is also a polar molecule. So this guy definitely will stronger. This is a polar molecule, so they're stronger than the boiling point. They have a higher intermolecular force, stronger than the non-polar molecule. So if you're looking at the non-polar molecule, then if you're looking at one of the options in the exam is a polar molecule, then definitely for sure this guy is stronger than the polar, then stronger than the non-polar molecule. That makes sense, right? And the strongest one is ionic, like sodium chloride. Have you ever seen any of the salt that is a liquid in the room temperature? You never see, right? So that means that this guy has a really strong intermolecular force. They all making a solids, right? Solids, they grab the molecules all together. So the intermolecular force is much stronger than the liquid, than the gas phase. That makes sense, right? So salts, those are all ionic compounds. They have a very strong intermolecular force than the water, than those gas molecules, oxygen, nitrogen, hydrogen, blah, blah. So if you're trying to melt the salt, probably the temperature is gonna reach more than 1000 Celsius. Are you clear? Okay. So this is generally how you represent, how you compare the intermolecular force between, if you can clearly to determine, okay, this molecule is a nonpolar, then the intermolecular force should be weaker. Then if you have a polar molecule, then it should be stronger than the other. Now, how do we determine if we have the both are, for example, if we have oxygen and nitrogen and hydrogen, those are all nonpolar molecules. How can we determine, I mean, those three, which one is stronger? Then you just need to look in their molar mass. The bigger size, the bigger stronger intellect force. Oxygen molar mass is 32. This is 28, and this is 2. So oxygen should have a stronger intellect force among all of those. Among all of those. The same thing you can do for the polar molecule. If both are polar molecule, you can also compare that. Okay, so those are, you see, if you're looking at the structure, it's a similar. Those are molecule. This first one is a methanol. And this is an ethanol, which is alcohol. And this is propanol. So the only difference is, see, those structure are pretty similar. They all has OH at the end. The only difference is they have one more CH3 attached on this structure. So if you're looking at this one, which one has a higher intellect force? This one has a higher intellect force because this guy has a bigger size. Okay, so this guy has a higher molar mass. You're just looking at the molar mass. So obviously, the last one has the bigger molar mass than the rest of others. So this guy should have a stronger intellect force. Okay, yeah. And this guy also, if you compare this one, if you compare this one and this one, which one is bigger? So obviously this one is bigger because this guy is a polar molecule, but this guy is a non-polar. The reason is this guy is non-polar is because we talk about if the organic compound, if they only made by carbon and carbon bonds, carbon and hydrogen bonds, that's a non-polar bond. Because carbon-hydrogen is a non-polar bonds, carbon-carbon also non-polar. So if this molecule only made by carbon and hydrogen, that's going to be a polar bond. Okay, what I'm talking about today is very important. It will show in the final. Okay. All right, so generally, this is the intellect force that I'm going to talk about. And if you're interested in this part in the Chem 2 class, I will also talk about more detail about intellect force. The last topic I'm going to talk is called the phase diagram. And this is the last concept that we're going to talk for the overall chemistry class. It's called the phase diagram. And I'm not going to talk too much about this, but I just need to give you one of the concept is phase diagram. The phase is what we talk about the gas molecule, liquids, and solids. And those are the three phases we usually can touch with. And just let you know, the phase, you can transition, the phase can be changed by changing the temperature, right? We know it, right? You increase the temperature, and generally you can change the phase from solid to liquid, from liquid to the gas, right? You decrease temperature, you change from gas to liquid to the solids. But actually, there's another way you can change the phase by changing the pressure. Even you don't change the temperature, just changing the pressure, you're going to changing the phase. In other words, for example, have you ever buy the one of the it's called air nozzle, a small tank containing the air, and if you want to clean some of your computer, the chipboard, and then you can spray the air, right? So that one inside of the tank is a liquid, right? That's a liquid air. The liquid air can be present in the room temperature, right? You bought this all in the room temperature. But you know, the pressure inside should be much, much bigger than outside, in the much bigger than the 1 atmosphere. So if you increase the pressure, generally you can change the gas phase of the air into a liquid phase. It makes sense, right? Okay, so this is how. In other words, if you want to change from liquid to the gas, you just need to decrease the air, decrease the pressure, which is the release rate. So that's why if you press the nozzle, and then you kind of like open the pressure inside to the air, to the outside, the 1 atmosphere. And then since the top part will have the same pressure like the environment, and then there suddenly just become a gas coming out. Okay, so that's it. So you just changing the pressure, you're going to changing the gas. Then you can change the phase. In another word, if you want to get a solid phase of the oxygen in the room temperature, you can do it. As long as you increase enough pressure, then you can making a solid air, solid phase of the oxygen. You can do it. Okay, so that's why you see you can see the dry ice. You can see the dry ice, right? Dry ice is the solid phase of the CO2. How do we make it? Make the pressure and make it. Okay, we can make it. So that's why the phase diagram here we're talking about actually containing 2D structure. This is a diagram between temperature and the pressure. Between temperature and pressure. So we can divide by the phase into 3 parts. Usually the phase diagram is like this. On the left side, this is a solid. In the middle here, this is a liquid. And then over here, this is a gas phase. So generally, this is what happened for the phase diagram. I can give you one example for water. The phase diagram usually is like this, but not always the same for the different molecule, different structure, different molecule. They could be different. Here, this is one of the example of the water molecule. Then you can see it. Several points I need to point out, and I think that's it. The red line over here is talking about the boundaries. And the red line over here, this is the boundary between ice and water, which is between solids and the liquid, right? So this line shows the boundary between solid and liquid. This line is between the liquid and the gas. And this line is between solid and gas. Okay, are you clear? Okay, so that's a boundary. Then, what does that mean if I show one of the dots on this? These dots, generally, they represent 2 values. One of the value for pressure, one of the value for the temperature. In another word, is that at this temperature and this pressure, we're going to show both phase, both solid and liquid, because this dot is on the boundary, and this boundary is between solid and liquid. So at this temperature and this pressure, temperature and this pressure, we're going to see 2 phases, solids and liquid. Are you clear? So if we have a dot shows over here, that means at this temperature and this pressure, we're going to show liquid and a gas phase. Are you clear? Then what does that mean if we have a triple points over here? So what does that mean? The triple points means at this temperature, which is 0.01 Celsius, almost close to 0 Celsius. And at this temperature pressure, very low pressure, you're going to see 3 phases. liquid, solids, and gas. So if we if we have this temperature and we have this pressure, you will see three different phases altogether. You're not going to see this three phases altogether in the room temperature, because the temperature in the real life, because we don't have that low pressure. This can only be seen in the experiment in an experiment in a lab. That makes sense, right? Yeah. So now are you clear what I'm talking about? Okay. So one of the questions they can ask is just say, okay, now you're understand the concept shows over here. Now I'm just saying, okay, so this is remember, this is solids, this is liquid, and this is gas. I'm going to have one dot shows over here, one dot shows over here, and one dot shows over here. So let's say A, B, and C. Okay, so if we from A to B, what is the phase transition? What's the name of the phase transition? From ice to solids, this is called the melting. Okay, from C to B, what is the name? Condensation. Okay, so if you forgot it, I'm going to remind you. There's 6 different phase change over here. From solids to liquids, this is called the melting. From solid to gas, this is called the sublimation. From liquid to gas, that's called the vaporization. Then if we have go backwards, if we have a liquid to solids, this is called the freezing. From gas to solids, that's called the deposition. From gas to liquid, it's called the condensation. Okay, so we have a 6 phase change over there. So in general, just need to understand, okay, what does that mean? If we have a one point to another point, what does it mean? Okay, so, you know, or let's say, if we want to change from B to C, what is the process we need to do? Okay, if we change from B to C, what is the parameter we need to change? From phase B to the phase C. What did you do? You increase or decrease the pressure? You decrease the pressure. You see, you decrease pressure, then we can change from liquid to the gas phase. Okay, we can change from the liquid to the gas. Okay, if you go from C to A, what are you gonna do with it? You need to decrease the temperature and also decrease the pressure, right? Then you can go to the A. So generally, this is the meaning of the phase diagram. Are you clear? Okay. So the phase diagram things, the practice is on the chapter, I think it's on the chapter 8 or chapter 7. The practice, it says practice that I gave you. Okay, yeah. You need to double check. Do you have it or not? I think I give that to you. If you don't have it, I still have the extra. So generally, this is pretty much things that I'm going to talk for the whole class. And in the lab time, I'm going to give you the practice for the final. And once again, if you have some of the lab you didn't have a chance to turn it in, then please turn it in. Okay, yeah. Yeah, so this is the practice, and you can, we have the answer in the back. Every, I believe every several picture, several pages, you will see the answer. Okay, so just a double tap with it. This is a photocopy of those, the real chapters. No, photocopy of those practice. It's not that here, I think most of those should be clear enough. Okay, if you have some parts that you didn't see there, there is, let me know. Okay, yeah. Some of the questions, I think this one, they only know color, only know one has a color, but this one, even without color, you shouldn't. You're not able to figure out what is what. How to solve this, okay? Yeah, so if you have the something that is going to show the colors, then you need to speak it. Yes. Okay, so please come over here on the graph one. And by the way, I recommend your work on the session from back to the front, because the front always, the session is in the one. You're doing good on one. But you need to have a more practice for the really concept. It's
That's what.